In this lecture, we're going to develop the more general treatment of the calculations of the rectangles that are called Riemann summations. Now, the basic idea, recall, is that the more rectangles you fit onto your interval, the better the approximation of the area under the curve actually is. So again, we can take a quick look at our parabola case from last time. Here, I have a parabola, and I would like to approximate the area under the graph and above the x-axis. So what I have here is, if I start with one rectangle, that's really not very good. But if I keep going, I notice that my approximation gets better and better and better. Now, somewhere at the beginning, I can still see the discrepancies between the area covered in green and the area that I want to cover, which is everything under the parabola. But once we get to a very big number of rectangles, then the two areas seem to already coincide. Now, the idea is, of course, not to have any fixed number of rectangles, but rather allow that number to go off to infinity. And we're going to have to build up tools to make sure that we can do that. So what I'm going to assume first is that I have the exact same parabola between 0 and 2, but now instead of subdividing it into any particular number of pieces, I'm going to divide it into n pieces. In this particular picture, the rectangles drawn are left endpoint rectangles. It doesn't actually matter which specific construction you develop the formula for. We're going to use left endpoints, but it's going to work just the same for any other ones. So first, what we're going to have to figure out, given any particular number, is what are my left endpoints here? How can I figure out their coordinates without going one step at a time? So I'm going to label these guys, and in fact, what I'm actually going to do is maybe create a more flat zoomed in version of this number line. So if I'm going between 0 and 2, and I would like to subdivide it into n pieces, then each piece here, dot, 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 is going to be of what size? Between 0 and 2. The entire length of my interval is 2. I would like to have n pieces. So each piece has to be of length 2 over n. So this guy is 2 over n, this guy is 2 over n, all the way up to the very end, including the last guy, who is also 2 over n. Now, this is great news. However, this doesn't particularly help me with determining their exact coordinates. Right? So before we do that, let me maybe come up with a labeling system that I will be able to carry out throughout. So the left here is going to be called x0. The next one is going to be called x1, x2, all the way up to x sub n. Now, if I'm going to use the left-hand points, then I need to know the coordinate of any given left-hand point in order for me to construct that rectangle. The first one is easy, maybe the last one is easy, but what about the ones in the middle? So if I want to calculate the fifth rectangle, and I know I need the fifth left-hand point in order to calculate the height, how can I compute that? What is the actual x-coordinate of my fifth left-hand point? Now, in order for me to determine that, maybe let me zoom into this picture a little bit and think about what happens on the, let's say, kth step. So instead of looking at the entirety of the picture, I'm going to zoom in on just one of these rectangles somewhere in the middle. So let's say I am going to look between x sub k and x sub k plus 1. So if I'm interested in the fifth rectangle, then my k is going to be 5. What I have in the picture is that I am constructing a rectangle on the left-hand points. So I'm going to take the left-hand point, go up to the function, which means my function is actually somewhere here. This is my y equals x squared. Then I'm going to go across this interval and down to x sub k plus 1 to construct my actual rectangle here somewhere in the middle. Now, let's label everything we can in this picture. So one thing I know already is that the width of this rectangle, this here, is 2 over n, because, again, my entire interval was 2, and I divided into n pieces. What about the height of this rectangle? That's really the only other thing I need to figure out, because I know the width already. Well, the height is I've plugged in x sub k into my function to figure out the height. So the height here is going to be x sub k squared, because my function in this case was simply x squared. So that means that I can now calculate the area of the kth rectangle. The area of the kth rectangle is, as it always has been, width times height. Now my width here is 2 over n, and my height is x sub k squared. Now, I feel like we can do better because, look, we can probably figure out what this x sub k is in terms of the starting point and what number of the rectangle this is. What I'm going to think about is, starting at 0 here, how many steps, each of size 2 over n, did I have to take to get to x sub k? Well, I had to take k steps. K steps to get from 0 to x sub k, and each step was of size 2 over n, which means that x sub k itself is k times 2 over n. Okay, one more time. K steps, each of size 2 over n, to get to my left-hand point of the kth rectangle. Now that means that I can use this expression to plug in for x sub k into here. So overall, the area of my kth rectangle is going to be 2 over n, k times 2 over n, all squared. Now, this is just the area of the kth rectangle. So somewhere down the middle here, I'm able to calculate the area. What I really want is the total area. So the sum of the areas of all the rectangles that I have built along the way. Here's where our practice with summations from a few chapters ago will really come in handy. I'm going to have to sum up over all the areas of the rectangles. So from the first rectangle, k equals 1, to the nth, the last one, sum of all the areas. The area of the kth triangle that we've just derived was this bulky formula. So this is what I'm going to have to sum all the way throughout. So I have 2 over n, k times 2 over n, all squared. And now I'm just going to have to massage the sum in order to simplify it as far as possible. Now, a few things to remember here. If the sum is indexed over k, then whatever is constant and not dependent on k can be, in fact, factored out of the sum. So first, I can actually just factor this square in order to see exactly what is constant and what is not. So I have 2 over n times k squared times 4 over n squared. And now I can see that the terms containing only the numbers and the n are constant with respect to k, so these can go outside of the sum. Okay, so this and this is constant and can in fact travel out. Whoops, so what are we going to have left? First of all, in front of the sum then, we're going to acquire 2 times 4, which is 8, and n times n squared, which is n cubed. And then I'm going to have the sum from 1 to n of k squared, because that is all that is remaining. Now this again is just a constant depending on the number of the triangles. And this sum is one of the formulas that we saw in chapter 6, the sum of all squares from 1 to n. This can be then just written down using the formula of the summation, and that formula was a little bit bulky, but not too bad. So the formula itself was n times n plus 1 times 2n plus 1 all over 6. Okay, so again, this expression is just exactly what the sum of squares from 1 to n is. Now, what I have so far is the total area calculated in terms of n, the number of rectangles. So that means that if you now ask me, well, what is the total area covered under this parabola if I use 100 rectangles? All I have to do, instead of carrying through the calculations all over again, is plug 100 in for n everywhere, and you will have your answer. Now, the idea though was the more rectangles, the better. So I don't want to have any particular number of rectangles. I would like to take the limit as n goes to infinity of this total area to figure out what's going to happen when I have infinitely many rectangles. So now if I take the limit of this total area, what are we going to see here? Now, this looks like it's going to be a bit of a nightmare in terms of calculating the limit of, but we can actually attack this using the dominating power analysis. All we have to figure out is what is the highest degree on the top and on the bottom in this particular rational function. So without actually opening up the brackets, what I would like to notice is if I were to open all of the brackets up, I have 3 brackets here, a term of n in each one. So the highest term I will collect is n times 2n. So the highest within these brackets would have been 2n cubed. So everything else is going to not matter at infinity. So I can note that this entire rational function, as n goes to infinity, will tend to 2n cubed over 6. It's important to keep the actual values of the constants though. Now what do we have here? Well, this looks a lot better because n cubes will just go away and all I have left are numbers. So what I have now is 8 times 2 over 6 or 8 over 3, which is approximately 2.6. It's a repeating 6, so 2.666 forever. This is now the exact area of the area under the graph of x squared between 0 and 2. This is a very standard process. There is a general formula that describes how to get to this expression without going through the construction of the actual rectangles, but the formula sometimes gets bulky and hard to really parse. Therefore, I usually prefer to do it in a step-by-step manner in order to really see where these computations come from. So let's take a look at another example where we have to go through this entire process that I've split into steps that are hopefully bite-sized. As I've mentioned earlier in the last lecture, this particular method is exceptionally useful for calculations of non-standard areas. And we often, in natural sciences, have to calculate areas that we cannot model as rectangles or triangles or anything like that. For example, areas of the surface of a leaf to figure out what is the total surface area through which the leaf can absorb, for example, sunlight. This can go to justify particular shapes of the leaf or particular structures within the leaf or the tree itself. First of all, given any particular leaf, we have to figure out how to model its shape. We're going to have to reserve the half of the leaf for actual function modeling, because if we model the whole half, this is not going to pass a vertical line test and therefore will not be a function. In this particular leaf's case, the function x times 1 minus x actually models it fairly well. Now, first thing we're going to have to figure out is what are the actual endpoints here? What are the intercepts? And for that, you cannot just assume it's going to be the thing that you want it to be. If you're given a function, find its x-intercepts. So in this case, either x is 0 or y minus x is 0, which will give you x equals 1. So the length of the interval over which we are going to be computing is from 0 to 1. Therefore, the whole thing is of length 1. Now we're going to try to find the area under the curve and above the x-axis here, so this particular value. What is the number of segments we're going to divide it into? Well, I would like to find the exact area, which means that I would like to divide it into n segments. Not any particular fixed number, but rather really infinitely many of them. That means I am going to take this, divide into many pieces. What is the width of each of these pieces then? Well, the length of the entire interval is 1, and I'm dividing it into n pieces, so the length of each one is going to be 1 over n. Now, just like in the previous example, what I'm going to do is think about a rectangle somewhere along the way, the kth one. So let's say this is x sub k and x sub k plus 1, as the endpoints of this little subinterval. What is then the kth value xk? If I start at 0 and I take k steps forward, each of size 1 over n, then of course what I'm going to get is k times 1 over n, or if you want to simplify it, maybe just k over n. Okay, so once again, k steps from 0 to reach x sub k, each step of size 1 over n. What is the height of that rectangle? So I'm going to take the left-hand point here. Again, it doesn't really matter, but we're going to stick with left-hand points. And in order to figure out the height, what that means is that I'm actually plugging this value into the function. Function is exactly what helps me to figure out the height or the y value of the corresponding rectangle. So if I plug in x sub k, what I have is x sub k times 1 minus x sub k, because that is in fact what my function looks like. But then the previous line here allows me to replace x sub k with a more specific number. So I'm going to put this into my calculations and see what that gives me overall. So I'm going to have k over n, 1 minus k over n. Now I can open up the brackets here in order to be able to better see what the overall number is. So what I'm going to have is k over n minus k squared over n squared. For the next step, what I would really like to do is figure out what is the area of this particular rectangle. The area, as before, is width times height. Let me note that. Width times height. And now I have expressions for both of these numbers. The width of my rectangular strip is 1 over n. So let's record that. And the height of it is this value here. The height is what I just had here. K over n minus k squared over n squared. Again, because we're going to be working within the sum, it's better to open up the brackets here to simplify this, to expand it out as far as possible. So I'm going to have k over n squared minus k squared over n cubed. This is the area of one rectangle somewhere in the middle of the way, not exactly the middle, but somewhere along the way. What I'm going to have to do next is add up the areas of all of these rectangles that have been built all throughout. So this is going to be my next step. The total area of all of the rectangular strips, I'm going to call it A, and it's going to be the sum over all the rectangles, so from 1 to n, of their respective areas. And we have just calculated that the areas were k over n squared minus k squared over n cubed. And just like before, now is where we actually utilize our familiarity with summations and apply whatever techniques we need to apply to figure what they are. So here, notice that first of all, I'm going to split the sum up into two, the first part, and then, the second part, so I can deal with them separately. But in either of the cases, the n squared and n cubed are just constants, so I will be able to take them out. So in the first summation, I can take out 1 over n squared, and what I'm going to have left is the sum from 1 to n of k, minus, from the second sum, I will be able to take out n cubed, and what I'm going to have within the sum remaining is going to be k squared. Now, both of these are the standard formulas for summations that we have seen, so I can simply apply those formulas. I'm going to have 1 over n squared remaining as the factor in front, and then the sum of numbers from 1 to n is n times n plus 1 over 2. Remember, this is the famous Gaussian derived formula. For the second one, I'm going to have 1 over n cubed times the formula for the sum of squares, which is n plus 1, 2n plus 1, all over 6. So once again, this is almost the last step, because in this step, if I know the number of rectangles I'm splitting my area into, then I'll be able to calculate the area exactly by plugging in the value for n. But I don't want any fixed number for n. I would like to take a limit as n goes to infinity. So what is that going to be? I notice that I simply have to take the limit of this number. That's what I'm calling a here. Let me maybe rewrite this here. As I take the limit of this number, I have two pieces to it that are being subtracted from each other. And in both of those pieces, I can again utilize the power domination analysis. So let's take a look at the first piece first of all. I'm going to keep 1 over n squared, but the top term here is something that I can reduce greatly. If I multiply everything in, the highest power term will be produced by multiplying n by n. So here, I'm still keeping the limit for now, but now my reduced first term is going to be n squared over 2 here. This term, the highest power of it, is in fact n squared. The second term, I'm going to keep 1 over n cubed. What do I have on the top here? This is similar to analysis we've just done earlier. If I collect the highest degrees of the n here on the top, I'm going to altogether get n times 2n. So in total, 2n cubed all over 6. That still is remaining. Now let's see what simplifications can I do within this limit now. Well, this n squared and this n squared get cancelled, this n cubed and this n cubed get cancelled, and what I actually have left over are just numbers. I have 1/2 minus 2 sixths, so 1/2 minus 1/3, or altogether 1 over 6. That means that this area below this function and above the x-axis is in fact 1 over 6. Now notice that if the actual question asks what is the area of the surface of the leaf, then we will say that the leaf area is double that, because I also need to account for the second portion here. We assume that the leaf was symmetric, which most leaves actually are, so I'm going to have to double my answer to get both sides of the leaf. It's going to be twice 1/6 or 1/3. So be careful that you actually answer the question that was asked in the beginning at the very end. This process is the process that you will have to go through every time you want to calculate the area under the curve using summations or Riemann sums. I will leave the next example for you to go through. It's split into the exact same sub-steps as the one that I have just covered, but this one is using the tapered leaf, so the leaf that looks like this, where the formula that for the function that actually models the top half of it is given by x squared times 1 minus x. Please go through these steps, fill them out the way that we did in the previous example in order to practice with the setup of the Riemann summations and with the actual manipulations with the sums and the limits of the sums themselves.